my people. Hope we're doing well. We're going to continue on doing some mechanics work for implicit differentiation, just talking about how it works. In the videos that follow, we'll be delving into implicit differentiation and how it helps us find the derivatives of inverse trig functions. And then later we'll be doing some application problems. Most specifically, we'll be doing some tangent line problems and maybe a few other things thrown in just for good measure. But let's go ahead and jump right into this. If we're differentiating with respect to x, I notice the fact that this is going to be chain rule right here. It's stuff cubed. So the derivative of stuff cubed is 3 stuff squared times the derivative of stuff. Well, the derivative of x is easy enough. That's 1. The derivative of y squared, we've seen that before. It's 2y prime. And the derivative on this right-hand side with respect to x is 3. Well, that's nice, because those 3's cancel out, and I'm left with a 1. I need this y prime to be freed up, I guess is the best way to describe it. So, I mean, I could distribute this x plus y squared to both terms and then subtract 1 to the other side and then divide. But, you know, you could just as easily go ahead and divide by it in order to free up the things that are inside this bracket. And let's go ahead and do it that way. 2y prime is equal to 1 over x plus y squared. Now this may not be the best way to do it, largely because this winds up giving you kind of winds up being ugly in form and probably not all that useful. And then of course I simply need to divide by 2y. So I get 2y x plus y squared minus 1 over 2y, because when I'm dividing by 2y, I'm multiplying by 1 over 2y, and it needs to be distributed to both terms, so it needs to show up in both denominators. And there you go. And if I had distributed this and used that form in order to isolate y prime, I would have gotten into a single expression, and of course this numerator would have been x plus y squared, and it would have been over 1. So I mean, it wouldn't have been too far off of what we got. And of course, it would have just been the result of getting the common denominator between these two, but it would have come out in that form. But again, like always, what form you need a derivative in has everything to do with what form it should wind up in, right? You want to put it in the most advantageous form for what you're going to do with it next. You know, if you're going to be asking it an output-based question, like, you know, well, Mr. Derivative, when are you 0 to find horizontal tangent lines? Well, then obviously it's going to be better for it to be in a single rational expression, because then you just need to set the numerator equal to 0, right? But as we go through it, we'll continue to talk about, you know, what forms are best for what. But just the straight up, you know, simplest form, that kind of starts to lose meaning when we get to calculus. So, which is why I've only been really requesting rudimentary simplification up to this point. Now, let's go on to this next problem. Again, here we need to remember that we need to do the product rule on this left-hand side. So the first times the derivative of the second plus the derivative of the first times the second is equal to y prime minus 1. Right? Because if we do it on this left-hand side, just do it term by term. This is the product rule from the left-hand side. Y times the derivative of e to the x plus the derivative of y times e to the x. And then the right-hand side, I simply do it term by term. Now notice I have 2 terms with y prime in it. So we can go ahead and bring that y prime over here to the left-hand side, and we can shove this non-y prime term over to the left-hand side, and we get that. Okay, well, you know, I like fewer negatives, so let's multiply through by a -1. When I factor out the y prime, I get 1 minus e to the x, and I have 1 plus e to the xy. I simply need to divide by this binomial, and I get this for my derivative. Okay. Okay, well, we're going to do something a little bit different for the last two problems. We're actually going to find the second derivative. Now, we haven't been doing a whole lot of second derivative stuff, but we will as we get into more application-based stuff and as we get to how the derivative impacts or helps us describe the shape of a function graph. But we've sort of done it sparingly up to this point because it's simply just doing the process again. In implicit differentiation, it's a little bit different. So let's go ahead and do this. Now, you may recognize that as a hyperbola, okay? And let's go ahead and differentiate. We get 2x minus 2y times y prime is equal to 0. Now, we can divide through by 2. We can shove the x over to the other side, divide by negative y, and I'm going to get x over y. Well, that's y prime. Now I need to do it again. And obviously this is in the form of a quotient, so I have to use the quotient rule. So y double prime, we start with the denominator, times the derivative of the numerator, minus the derivative of the denominator, times the numerator, over the denominator squared. And you're like, well, that wasn't too hard. Yeah, but I have y prime stuck in here. And I really need it in terms of just x and y. So what happens is I need to take this expression, which is equivalent to y prime, and I need to drop it in here for the y prime. So I get y minus x over y times x over y squared. That is simply a complex fraction. I deal with it the same way that I deal with all complex fractions, by multiplying through by the denominator that's problematic. I'm going to get y squared minus x squared, all of that over y cubed, and that is y double prime. Okay, and you just need to remember, once you get y double prime, that's usually not the problem. The problem is you need to then substitute and simplify. So actually the difficult part of this is, again, not the calculus, but the algebra that's involved. And that shouldn't be too frustrating, but it is something that you just need to take into account, right? Okay. This is going to be a short video because this is the last one for this. I'm going to go ahead and call it quits after this problem and start a fresh video for introducing inverse trig. Okay, again, this right here is a product. The 4 can come along for the ride. Some of y'all have actually sort of grouped it. When you had something like this, or when you had a product with a numerical coefficient, you kind of grouped the 4 with one of the functions. That's fine. You can, that doesn't really matter. I usually just sort of put it out here, and then because I just want to deal just with the x times y. So I get x times y prime plus 1 times y, and then over here it's 2x, and we've seen this enough times to where it ought to be y squared becomes 2y prime. Okay, I can divide through by 2 if I want, and that becomes 2 over here. This becomes 2xy prime plus 2y is equal to x plus 2y, or not, sorry, that 2 is gone, y prime. Okay, well, let's gather all the y primes over here on this left-hand side. So basically this guy I need to shoot over here. This guy I need to send over to the right-hand side. And so I get 2x y prime minus y prime is equal to x minus 2y. Again, factor out the y prime and divide, and I'm going to do that in one step, 2x minus y. Now, as you can see, taking the second derivative is going to be a little more involved for this one, so I'm going to kind of scoot over here to the left-hand side in case I need to come up here and start another column. So I need y double prime. I need the denominator times the derivative of the numerator, so that's 1 minus 2y prime, and then minus the numerator, x minus 2y, times the derivative of the denominator, and that's 2 minus y prime. And then, of course, that's all over 2x minus y squared. Okay, now here's where it just gets a little bit cumbersome, okay? So we need to FOIL both of these. And so we're, first, outer, inner, last, right? And I'm going to keep that negative at bay, and I'll distribute after I'm done here. So first, outer, inner, last. Okay. Doesn't look like I'm going to have much room here in that other column, but we'll deal with that when we get there. Okay, so let's go ahead and just distribute that negative. Now the 2x and the negative 2x cancel out. That's kind of nice. Basically, the 2y prime and the negative 2y prime, they cancel out. And then here we're going to get negative 4xy prime and positive xy prime. We're going to get negative 3xy prime. And then negative y and positive 4y, so plus 3y over 2x minus y squared. Well, thankfully, one of my y primes canceled out, and I was left with only one y prime in order to plug in. So this is what needs to go, and I'll kind of loop it around this way this time. It needs to go right there. So I get negative 3x times x minus 2y over 2x minus y plus 3y, all of that over 2x minus y squared. And again, it's merely a matter of resolving the complex fraction. So, 2x minus y over 2x minus y, being careful to distribute it to both of these terms, right? And so I'm going to get negative 3x times x minus 2y, canceled. That was kind of the point. And then 3y, 2x minus y. Sort of, probably should have started another line, but you can see it. And then that just makes this 2x minus y cubed down here. You could probably leave it like that, but let's go ahead and see if it simplifies nicely. 6xy plus 6xy minus 3y squared. Yay! Looks like it's going to be kind of nice. And so we can go ahead and pull out a negative 3. That's going to be x squared minus, and of course these are going to combine into 12xy. When you pull out a negative 3, it's going to become negative 4xy plus y squared, and that is all over 2x minus y cubed. And unless I've made an arithmetic mistake somewhere, amidst all of that analytic toil, that would be my derivative, okay? And so basically what you need to do is you need to get your y prime, find y double prime, substitute your y prime expression in, and resolve any simplification problems that arise once you do that. We'll do a couple more examples in class, obviously, but I wanted to go ahead and at least put this out there for y'all to see before we start moving beyond simply the first derivative mechanics of implicit differentiation. Like I said, the next 1 or 2 videos is going to be inverse trig, and then the couple of videos after that are going to be finding equations of tangent lines and other application issues for implicit differentiation. So be on the lookout for those. As always, if you have any questions, please do shoot me an email. Bye.